Hello and welcome to Computer Tech and More. Today we're going to be taking a look at the Iceberg Thermal IceGale Extra 120mm class fan. This is my Read Undear series. Let's get right into it. So just a general explanation of what this video is actually going to be. Well, I did a complete retesting of all of the fans I previously tested using a new noise testing methodology. Previously, I had the microphone placed really close to the fan blades, and I feel like I was picking up noise interference between the fan blades acting around the microphone itself, or potentially just the air rushing past it. Either way, I think it was causing spikes in how much noise each fan was generating, making it less consistent. But that doesn't mean that the data is useless. It just limits how it can be used. So the use case for it would be in a pull configuration on a heatsink. Most radiators or AIOs have a little of extra space, so it shouldn't be as applicable there, but it may very well be. But definitely on a heatsink where you might be pressed up against the fin stack, or if you are putting it at the front of your case and you're up against the mesh filter, like it's just right up against the fan, that'd be the other case that my original testing methodology would be applicable. The new testing methodology places the microphone at a fixed distance away using a pull, so I get the same distance every single time by just sticking it between the two things, and having my sound dampening panels around it, as well as waiting for my house to be at within a 2 decibel range of each other in testing. So I'm just testing in my home office, so I wait for my house to be quiet, my neighbor's AC unit to turn off, all that kind of fun stuff. So my previous test methodology, I found that it was accurate within plus or minus 4 decibels, so that is an 8 decibel range. That is pretty large, because keep in mind that every 10 decibels is a doubling in noise value. My new test methodology gets me accurate within plus or minus 2 decibels. I would like to further enhance my testing methodology to take it to the next level, where I'd be making a sound isolation chamber, so it'd be small, not like the other big channels are doing. A upgraded anemometer that can read at higher accuracies. Unfortunately, that is substantially more expensive, like $500. I want to get a better microphone. Right now I'm just using the one I'm using to record my voice on. I want to get one that's dedicated for noise testing, and upgrade my test box and other bits and bobbles, as well as being able to purchase more fans. But I can't do without help from viewers like you to subscribe to this channel. I greatly appreciate the help with subscribing to my Patreon page. I'm still figuring that side out. And or sponsors. That's the only way I can take my testing to the next level, to be basically absolutely the best on the internet. Anyways, let's move on. A little bit of explanation of what we're going to be looking at. On the right side of the graphs, we're going to have the original testing methodology. It's rank, the model of the fan. They're in alphabetical order. The RPM was running at for the noise normalized value, and the airspeed that it was running at. And same sort of thing with the new testing methodology will always be on the left side. For 100% PW fan signaling, you're going to have the rank, fan model, RPM, noise, and the airspeed. And all the tests can be directly compared with each other, except for CFM, or not compared with each other. 120s and 140s can be directly compared with each other, except for CFM testing, where 120s and 140s use a different testing apparatus. All right, now that my little bit of explanation is out of the way, let's get right into the comparisons. All right, first up is noise normalized testing through my CPU AirCooler, the U12A, and just because I haven't said it yet, I'm going to go into a detailed explanation of what each test is, why it's important, and other details about it in the second half of this video. Right now, this is just an overview, so if you're new to this channel, I recommend that you actually watch the detailed explanations. If you've been here before, well, you can just get the new data and compare it to the old data and move on. Or I encourage you to watch actually the detailed explanation, because, well, that's half the video. Anyways, AirCooler, originally the IceGale Extra was ranked 11th, running at 800 RPM, 1.6 meters per second of airflow. It is now ranked 12th, spinning at 606 RPM, moving 1.2 meters per second of air. So it lost one position, 200 RPM, and quite a bit of airspeed overall. But it's not a bad result. And at 100% PW fan signaling, it retains its position at first place because of that ridiculous 3,000 RPM. In cooler testing, its value proposition, it was ranked 12th overall for noise normalized testing. It is now ranked 16th, so it lost quite a few positions there. At 100% PWM fan signaling, its value proposition ranks it rank 5th, which is a great position to be in, no change. In CFM testing, it was originally ranked 34th. It is now ranked 45th. So it lost a lot of positioning there. So it's not great in this noise normalized value part. At 100% PWM fan signaling, it is ranked 3rd overall. In the value proposition noise normalized CFM testing, it was ranked 30th. It is now ranked 38th. And CFM 100% PWM fan signaling, it was ranked 10th and retains that position. On to case simulation airflow testing, the 6-inch mark, noise normalized. Originally, it was ranked 32nd. It is now ranked 41st, so that is a pretty large drop overall. At the 11-inch mark, it was ranked 17th. It is now ranked 28th, so again, a pretty large drop overall. Its value proposition for the noise normalized value, 6-inch mark, it was ranked 29th. It is now ranked 32nd. For the 11-inch mark, it was ranked 19th. It is now ranked 22nd. All right, we finished going through the new versus the old. Let's get into the detailed graph. So first up is the case simulation test. The case simulation test can be looked at in a couple key different ways. And the first way that I'm going to talk about is how good is this fan at actually blowing air? So think of it as a fan analysis. The most perfect fan in the world would not lose any airspeed from the front of the case traveling all the way to the back of the case. It would maintain a perfect airspeed. But we don't live in a perfect world. Air slows down. So this is actually for a ceiling fan, but I found it very applicable. So air in the room, or in your case, will slow down the edges, and eventually it'll slow down into the middle. So kind of an inverse cone shape while it's spreading out and the cone shape going out. So what you want is to have it slow down as little as possible. And to do that, you need a more focused airflow. So if the airflow is spread out wide to begin with, it's going to slow down more quickly because it's not concentrating its airflow. So older style static pressure fans did this wide pattern. Personally, I think that all fans should be this concentrated airflow. And while I'm thinking about it, if you have a radiator and you have the fan in a pull configuration, the airflow pattern coming out the fan will be the exact same as if it was a case airflow fan. So just pushing air into the case. The only difference is that the fan will have a higher restriction, so it probably won't be blowing as much air, but the pattern coming out the other end will be the same. If you have the fan in a push configuration, so you have the radiator on the back side of the fan, then the radiator and also a heatsink will straighten out the air, so the air actually coming out of it will be a nice tight line pattern, not line, but a nice tight straight pattern. And in fact, it's straightening out the airflow. So just as a general thought. So my general analysis here is actually more focused on air coolers than radiators and AIOs, but certain aspects of it are applicable. You still want to get the air through the case, but you want to retain as high an air speed for whatever case you're buying for when the air hits your heatsink, basically. Even though there's a fan there, you want the air hitting the fan to be moving at as high a speed, relatively speaking, as possible, so that it blows air more efficiently through it rather than having to pull the air in. The air is already there. So you don't want to cause more work on the fan than you have to, is in essence what I'm saying here. So the second way to look at it is, what size case do you actually plan on buying to know where to focus your eyes on this data set? Are you buying a small form factor case? Mind, this would be a small form factor case that is still a front to back airflow with an air cooler that isn't drawing air from the side, it's drawing air through the case. Or are you putting fans at the bottom of your case and you're blowing them up into your GPU? So something like the bottom fans in the Fractal Design Torn. That's where the 6-inch mark would be ideal. And just as a general note, small form factor case that this isn't applicable to would be like the Fractal Design North is the most recent one that pops into my brain, where it draws air in from the sides, blows it out the top, draws in air from the bottom, blows it out the top. The 6-inch mark is not applicable with that. You would actually want to look at the data set for my CFM testing and for my heatsink testing because small form factor cases tend to be more like a pressure application, and those two tests lend themselves better to show how good the fan is at dealing with pressure, meaning static pressure behind it. The 9-inch mark is representative of a compact tower. Again, standard front to back airflow, just kind of shrink down and smaller than what the 11-inch mark is. The 11-inch mark is a mid-tower case. A mid-tower case is something like the Fractal Meshify 2C, the 550D, the Corsair Stormtrooper looking case that comes in white and black. I don't remember the name of it. It's part of their 500 series, I think. And then we have the 14.5-inch mark. The 14.5-inch mark is representative of a large tower, something like the Fractal Design Torn. Actually is very representative there. So depending on what size case you have is determinant for which data point you actually want to focus your eyes on. And of course, these data points do indicate how effective, what I was talking about before, a fan is at blowing air. So the steeper the drop off, the worse designed the fan is. What you don't want to see is starting off really fast and then dropping off very sharply to 0 even before the 9-inch mark. That indicates a terrible performing fan. So again, you want it as flat as possible and as linear as possible. Well, these data points are all fine and dandy. They're at the 20, 40, 60, 80, and 100% PWM fan signals, but I've got nothing to compare against. Well, that's where the next graph comes in. In teal, we have my control fan. It is 3 parts A12X25 to 1 part A14. So it just gives me a blended fan to get mixed results because 140s tend to do better at the longer distances, so the 11 and 15-inch marks, while at the 6 and 9-inch marks tend to be better for the 120 millimeter class fans for whatever reason. So doing that gives me like a quote-unquote 30 millimeter class fan. So just a blended result to get a good mixed data set. Good fans would be considered near that line and over it. Worse fans are considered underneath it. So the IceGale Extra right here is in this blue line, and it is pretty poor performer overall, I'm going to say, in noise normalized results. The P12 Max is not looking much better, and the NF F12 3000 IPC is also down here with them. And it's kind of funny how the three fans actually almost have similar-ish looking results despite 3 very different blade designs. And remember, this is noise normalized at my 12 decibel mark. Next up, 100% PWM fan signaling, so brute force wins. My control fan would be spinning at effectively 2,100 RPM. So this kind of goes to show how inefficient certain blade designs are. So the NF F12 is moving relatively little air for its 3,000 RPM, especially compared to the other 2 fans, indicating that its blade design really is not designed for case airflow, so don't use it there. But focusing in on the IceGale Extra, it has a very high top end, so its short throw distance is incredible, but it just drops off so quickly that by the end of a bigger case, you're actually better off getting a P12 Max for a larger case. So I did choose the 3 other fans on here just as a brief comparison because they are other 3,000 RPM fans. Next up, how do they compare against, well, other fans? So this is an extended data set that drops out my control fan. Noise normalized results. The IceGale Extra is right here, shifted towards the bottom, but not dead last. And noise normalized results is actually starting airspeed is pretty pitiful, but then it doesn't lose much airspeed. Drops a little bit between the 9 and 11, and then kind of a slow descent. So there are many fans that actually drop off far quicker, like the Silence 4 Pro, but they're just other fans that are more effective at blowing air, as seen at the top of the graph, and you can color match it. How about 100% PWM fan signaling? Well, the IceGale Extra does sit at the top of the graphs, especially for shorter distances, but as we get farther away from the fan, it drops off pretty steeply. Once again, we have the P12 Max listed in here, spinning at its maximum RPM. But surprisingly, the Silence 4 Pro is actually holding its own pretty well. And then, I don't know, we can see some other fans, but it's definitely better than my bottom performers, like the S12B. Next up, the 9-inch mark. So a brief explanation. So you can see that fans that tend to drop off steeply tend to drop off between the 6 and the 9-inch mark, but they're not completely terrible yet. So I have a harder time measuring air speeds under 0.5 meters per second. Just that's where my anemometer becomes less consistent, which is why I want to upgrade it. But again, the next one costs $500, so I really do need that support to get me to the next level, to collect the next set of equipment to get you all the best data possible. But the 9-inch mark was chosen because the fans that do suck at blowing air in a concentrated air pattern haven't completely dropped to zero yet, while the ones that create a good airflow pattern are still holding their own, so you'll see a larger relative difference between the fans. So the IceGale Extra, you'll notice that it starts off at 0 and then has this linear line. That is because I could not get the fan to function at its 20% PWM fan signal. There was just nothing there. So the minimum is actually 30, but I needed this data point to extrapolate what its effective speed, RPM, would be for noise normalized results, because its first data point was already so noisy that it was over my minimum. So this is a calculated noise normalized value as opposed to a true noise normalized value, as you can see from most other fans that have a much wider data set. But what do we see with the IceGale Extra? Well, it is basically sitting in the middle of the roads. It's actually doing relatively better compared to most other 3000 RPM class fans. So it indicates it's actually not terrible in its noise efficiency, but it's just not as good as some other ones. But if you just need raw brute force, lots of airspeed, it really is that good, especially at shorter distances. Next up is airspeed through my CPU AirCooler. My cooler is, once again, the U12A Noctua cooler. It is a single tower. I use one fan on the front of it. And on these graphs, we have on the left side RPM versus or airspeed versus RPM. On the right side, we have airspeed versus noise. And both of these graphs, better fans are going to be sitting top left, worse fans are going to be sitting bottom right. The left one is basically a blade efficiency. It is how good is this fan at pushing air at a given RPM. So in effect, you want it to be as high as possible on this graph. You want the least amount of RPM for the most amount of airflow. That would indicate better performance. So let's take a closer look at what we're seeing. So the blue line here is my control fan. The red line is the F12 3000 IPC, the purple line is the P12 Max, and the green line is the IceGale Extra. So this indicates that the IceGale Extra is actually a very effective blade design. It moves a lot of air for a given RPM, much better than any of the other fans. With, let's see, second place belonging to the NF F12, and then the P12 Max. So this is where the F12 kind of comes into its own, being quite effective. On the right side is noise versus airspeed. So this is how much air can the fan push at a given noise level. So again, a noise efficiency. Well, the blue line is my control. The IceGale Extra is actually kind of sitting in line with my control fan, indicating a actually very good design. It's just that it spins so fast initially that it's already noisy. So it's kind of up to you if you think that if you can put up with the noise level that it starts off with, this will give you extreme performance. But again, you have to start off with that noise. While the P12 Max slightly outperforms it noise-wise, not substantially, but slightly. But it starts off at it starts off at a little bit lower noise level. So again, you have to choose what's most important to you. And then the NF-F12 3000 starts off with the lowest noise value of these 3000 RPM fans. But it is underperforming compared to my control fan pretty heavily overall, I'd say. But how do they compare with each other? First, a brief explanation of my key on the side. So you'll notice some numbers like 225 W, that's watts, equals 2. So I did a testing piece where I let my CPU run a CPU-only load. It was actually a handbrake conversion test, so it's just running that. And I adjusted my fan RPM. I let the CPU clock as high as it could go to thermal max. That was 90 degrees on my i7 11700K. So it just stayed at that 90 degrees. And I would back off the PWM fan signal and measure the airspeed coming out the back and measure the sustained wattage that the CPU could draw at that airspeed. So I was looking for that steady state mark over and over again at each PWM fan signal. So I got an estimated wattage that my CPU could draw at a given airspeed. Now, this is applicable to both my CPU, the 11700K, because every CPU's wattage is slightly different and how it applies heat is a little bit different. So if it doesn't fully engage all the heat pipes or which heat pipes it engages the best, will cause variation between CPUs to CPUs. So it's applicable to my CPU and it's applicable to my cooler. So if you don't have the U12A, these wattages won't line up at all. So then you'd be saying, well, then how can I use this data? Well, let's say you have the FK120. It's moving 0.6 meters per second through my cooler. But if you upgrade to the iceberg thermal extra noise normalized results, it's moving 1.2 meters per second of air. Well, for your CPU, your cooler, whatever, I don't know what extra wattage you will get, but you will be able to draw extra wattage on an unlocked CPU while retaining the same temperatures. If you've got a locked CPU or you've limited the maximum clock speed and you're running at really high temperatures, well, having that extra airspeed overhead means now that your CPU is running cooler for that clock speed, that wattage, that power draw. Or you could take this extra overhead, not for the IceGale Extra, but other fans. You could take that extra overhead and back off the PWM fan signal and run your fan quieter. So these are how you can use it. So now that all that explanation is said, how does the iceberg thermal extra do? Well, this is an extrapolated result using calculations, so it's not real. So thus it is actually terrible. But using its calculated value, it's not bad. It's just that its minimum RPM for me was unreadable and the fan would stop at 20%. So it's noisy to begin with. How about 100% PWM fan signals? Again, the wattage for airspeed is on the side. It's all the same. The IceGale Extra is the king. It even destroyed the T30 for me. Now, I want to note something in particular. I'm using an AirCooler. Mine, the U12A, has fairly tight fin density, so I don't know how well it will compare to a thicker radiator. I'd like to add that to my testing suite. But again, all of that costs a lot, so viewer support, please. But this indicates to me that the IceGale Extra is actually the new king of radiator cooling, assuming you don't want it to run quietly. The T30 has a much wider range of PWM fan signaling than the IceGale Extra. And you can see how other fans ranked in here. It's a small sample selection of other ones I've tested for the... And again, this is the 100% PWM signal. So next up is airspeed versus decibels. Better fans are going to be sitting top left, worse fans are going to be sitting bottom right. And how does the iceberg extra do? Well, it's actually really good overall. So it is sitting towards the top of my subsample selection for this graph. Again, we have to ignore this bottom part, but it's really quite up there. It's very effective. I would cautiously say I'd recommend it. But if you watch my original video, I do have hesitations for the design in that the motor kept revving up and ramping down, and the fact that I couldn't get the fan to work outside of BIOS. The moment I'd boot into Windows, the fan would stop spinning altogether, no matter what PWM fan signal I set it at. IceGale full config. And next up is my CFM testing. So CFM, a lot of reviewers use it to talk about case airflow testing. This is fundamentally incorrect. It is a valid measurement for measuring airspeed through a cooler, for measuring airspeed through a tube, for measuring airspeed through the entire case, but not airspeed or CFM inside your case. And the reason for that is it doesn't take into account the airflow spreading out. So in essence, what a CFM test is you know the diameter or radius of a tube. So you know r squared times pi. So if r is in feet, so that's feet squared. You know the airspeed going through it. Let's say that's in feet per minute. So feet per minute times feet squared is feet cubed per minute, or cubic feet per minute, CFM. And in my CFM testing, the fan is the exact size of the diameter. So as the air blows down, it has got no room for the air to spread out. So a fan designed to blow air off to the out to the sides versus one that's designed to focus the airflow, they're going to look much more similar in performance blowing air down the tube than they would in my case airflow testing, which is why this isn't valid for case airflow testing. It hides results. Other reviewers who do it just don't understand the science. Now, where is it applicable? If you want to build your own at-home wind tunnel, you can hook up your fan, put it in the tube, and you want to be able to measure varying airspeeds coming off the back, you've got your own at-home wind tunnel. If you want to measure PQ curves, so pressure airspeed basically. So as pressure increases, airspeed decreases, yada, 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 vice versa. You would have a restrictor over here somewhere, and you would open and close, you'd have some pressure monitors on it, and you'd be able to measure the static back pressure. Noctua is known for doing this type of testing. It is very valid for doing that testing because you're actually looking at the pressure for this fan going through a heatsink, a radiator, of varying thicknesses to generate your PQ curves and estimations that way. And the last way isn't coming to my mind right now. But you can also use CFM for, again, measuring total airflow going through your case. So like my Fractal Design Torrent, I can measure the airspeed going out the back of the case. I don't have any back fans. I just have the CPU air cooler and the front fans and the bottom fans. I didn't attach a back one. So I could measure the total airspeed, or average airspeed, traveling out the back of the case and generate a CFM for the total case. Or if you have your case set up like a chimney. So radiator at the top blowing air out, fan sucking in, let's say you had no fan in the back. You could calculate your total CFM going out of the case. So that's just other ways to use the data that are valid and like real, not fake shenanigans. So I don't like these graphs to begin with for case airflow, but it is very valid for heatsink radiator type testing. So we're going to move through it fairly quickly. RPM versus CFM, noise versus CFM. We want to stay close or over to the top left of my control fan. And what do we see? All three fans listed are very close to my control fan, including the IceGale Extra. When we start taking a look at noise versus CFM, all three fans are a bit under my control fan, except for the P12 Max. It is proving to be the most efficient in this test. Next, noise normalized results. The IceGale Extra is at the bottom of the graphs, not a great position to be in. But at 100% PWM fan signal, it is towards the tops. So it's actually kind of interesting here that it did really well in the airflow test, but in the CFM test, mind, my CFM test isn't perfect CFM testing. It's more of a CFM pressure test because my tube is so short that when my anemometer is in position, it actually causes back pressure in front of it. So it's not a perfect test, but it does indicate that the T30 is better than the IceGale Extra in this type of testing that's quasi-pressure. So again, it's kind of indicating mixed things, and one reason why I want to upgrade this whole testing methodology. So then we have CFM versus decibels. The IceGale Extra is pretty bad, so let's just move on to the next section. For value proposition, the IceGale Extra is a $20 fan. On all the following graphs, we're going to have the noise normalized results on the left side, 100% PWM fan signal on the left side. And who are these graphs most specifically for? Well, if you're trying to pinch every penny, so you're trying to get the maximum amount of performance for the least amount of money, you're going to want to pay special attention to these graphs because they are going to be the most important to squeeze every penny you can out of your build. If you've got a little bit more budget where you want better noise performance, you want better overall airspeed performance, or you want a little bit of RGB bling or some other specific styling, that's where you take this data, compare it to the earlier graphs, and determine which fan suits your needs the best. And if you've got unlimited budget, well, buy whatever fan you feel like because you have the money to buy whatever you feel like. So all of that said, the Iceberg Thermal Extra, IceGale Extra is very bad in noise normalized results. So let's just move on. At the 6-inch 100% PWM fan signal, it is ranked very well overall in its value proposition, but it isn't the top value pick. The TL-G12 is by far the best, and you can see where other fans rank as well. How about at the 11-inch mark, noise normalized? Well, it's okay, but it's, again, the minimum RPM on it is inconsistent, so it may be too noisy at that low PWM signal. How about the 11-inch mark at 100% PWM fan signaling? Well, it's right up towards the top, but it is still not the top value pick. So you need to choose what is most important to you in your build. How about through CPU air coolers? Noise normalized results. And again, value proposition is airspeed divided by dollars. So it's performance per dollar. The Iceberg Thermal Extra is better than average, and at 100%, well, it's pretty well up there, but again, it's not the top value picks. The P12 Max and the TLG12 are way up there. How about CFM testing? Well, it did pretty badly noise normalized. How about 100%? Well, it did better at 100%, but again, it's just a far cry from the best, like the TLG12 and the P12 Max. So where does that leave us with this fan? Well, I found its signaling to be inconsistent, the motor revving up and revving down when held at a constant PWM fan signal. The fact it wouldn't run outside BIOS. Mind, I was using like 4 fan extenders just to get the fan out of my case. Other things to need to buy is a dedicated test system. So that could be part of the reason. It requires a very high amperage. So if you need to move a lot of airflow, it is definitely a great pick. But for me, I just feel like there's too many compromises going with this fan. That is my personal opinion. And you're welcome to do whatever you want. I'm just here to try to give you the data as I see it, and then at the end here, just give you my general opinion. Let's move on to my wrap-up section. Alright, at the end of every video, I like to show off the raw data. You're welcome to use the raw data if you would like to for your own personal use. If you're going to use it in any sort of publication, journal, written, video, anything, I do ask that you reference me and my channel. I'm the one who generated this data, and this data belongs to me. But if you want to use it for your own purposes, again, for making your own graphs, charts, comparison analysis, you're welcome to do that. You just need to copy it down. Each fan takes me about 1.5 to 2 hours to do this level of testing that I'm currently doing. And then it takes many more hours to update my graphs and charts in this Excel table, as well as then create the presentation and then, of course, record it. So I do appreciate you referencing me and my channel. If you've got fans you'd like me to check out in future videos, please leave them in the comment section down below. If you've got constructive criticism for me on how to make my videos better, I take all feedback very seriously and try to improve it. Just note that it may take me a little while for it to roll into the next videos, as I tend to test and then record in large groupings. And I don't know. Check out my Patreon page. Please subscribe. And I hope to see you next time here on Computer Tech and More.